Hi. We're the LN2 vaporization team. We're looking to do testing this weekend with just air and some of the setups that NASA uses. Do we need any like special fluids for that, or do we need to go ahead and
Talk to the, especially
Okay.
Yeah, he's in charge of safety.
Okay.
And he'll make sure that he recognizes you actually know what you're doing. Not to turn on.
I can feel it too, I can stop.
Yeah. Sounds good. Okay, we'll check with that. Alright, check with that.
Yeah, they were reenactment of Anton Churga's memorial.
Okay. Alright, sounds good. Thank you.
I should watch that movie again. It's been a while.
That was my sister. If you have an idea how
Okay, so let's start. So last time on Tuesday, we have seen the probabilistic view of expander. Basically, so we have talked about random walk and lazy random walk. And can you remind me what is this matrix? Lazy random walk matrix that encode how lazy random walk is? A D inverse. Plus what again?
Plus I by 2.
Yeah, great. Right. And we have also seen that, so from this walk, if you have some distribution, then if you do if you have some distribution on vertices and you apply the walk, then you get a walk on the next step. And we have seen that the limit when t is going to infinity of this, basically like pt, where this is just this is what? This limit. Yeah, it's degree vector and normalized by this. Yeah. And also we have seen how fast the probability converge to this degree vector, and we call this pi. And yeah, what dictates how fast the probability converges to pi? Yeah, great, thanks. So the chip. Basically, what we have seen is here. So this is the deviation from pt and pi on each node v, on each node b. And if lambda 2 is big, which means that the graph is an expander, then the deviation really decrease exponentially fast, right? And then and we have talked about mixing time, which is basically it's the time that you guarantee that after this many steps of random walk, then the distribution pt really come close to pi, where the total variation is at most epsilon. And then we say that we have seen that the this mixing time is essentially 1 over lambda 2 within log factor. All right, and then I mentioned quite quickly about two application of random walk. One is that if on expander, if you would like to find a path of logarithmic length between any two nodes, you can spend just root n time. You don't need to read the whole graph. So that's one. And another one is that not just on expander now, if you want to check connectivity between any two nodes in undirected graph, then you just need log many bits of space. And actually the time is n to the fifth, something like that. And by the way, so I want to stress that, and the algorithm is just very simple, just keep doing random walk until you go from S to T. I want to stress that this really works on undirected graph only. Yeah, so it is open if you can do it in an indirected graph. But we can prove that if you just keep doing random walk, it wouldn't work. And the reason is that you can consider this graph where is a path, is the directed path. Suppose this is S and this is T. And then now you create this thing. And you can see that it would take, if the length of this path is n, the probability that S can reach T is something like 1 over 2 to the n. It's very small. It's exponentially small. So you would need exponential time for a random walk from S to visit T, even if this graph is strongly connected. Yeah. And yeah, as Aditya said, it's open if you can. There is an algorithm that can take log n bits of space to check the connectivity in an indirected graph. But actually, this leads me to to mention one very nice open problem. That is, this is open too. So let forget log n bit of space. So what if you want, so in directed graph, use space of n to the 0.99. Even this is not known. And the best known is it's not something people can guess, but it's something like this. So this is better than any polylog, but it's not. This is not a polynomial factor. So and this is open even if even with randomization, this is not known. Yeah.
The best case is deterministic.
And this is deterministic. Yeah. And if you just want something like ON or n log n, something like that, then do some space efficient depth first search should be enough, something like that. But there is a better way to do it. And yeah, so this is a very interesting open problem actually. It's hard to believe that you cannot do it, but it's have been open for a long time. And yeah, if you want to think about it, let me know. I want to think about it too. Okay. The last thing I want to tell you quickly is about sample a spanning tree, where here you are given a graph G, and you want to sample uniformly a spanning tree in the graph. And now I'm going to tell you a super simple algorithm. Okay. The algorithm is like this. So I need to tell you one thing first before telling you the algorithm. Actually, I need to tell you what is a flip operation. So suppose you have a graph, and then let's say you have any arbitrary spanning tree. Okay, call this T. Then you can, if you look at any non-tree edge, so some edge outside the tree, so maybe something like here. So this, if you look at this edge, then it would create some unique cycle inside a tree, right? And then what you can do is you can choose any edge in the cycle, and let's say this guy, and delete it. So if you add E and minus E prime, then you get a new spanning tree. So this is what I mean by a flip operation. Just add one edge, delete one edge in the cycle. Okay. And now from this flip operation, it creates a relationship between two spanning tree. And you can think of this as it induces a very big graph, where a very big graph G here, where each node is a spanning tree, and you add an edge between them if T can be flipped to T prime. Okay.
What do you mean by each node is a spanning?
So.
Oh, you are representing every spanning tree.
Yeah. You create a very big graph where each node in this graph represent one spanning tree in normal graph. Yeah. Okay. So this is like a sum graph. It is exponentially big, right? It's like something like 2 to the n or more, like n to the n, something like that maybe. However, this script G here turns out to be expander. And this is like one of the special case of something more general. So one can talk about matroid and create some graph based on that matroid, and that graph is an expander. So doesn't matter if, like, I just want to throw the word matroid to you, that it has some connection to matroid. But for this context, this graph is an expander. So it means that if you do like a log, like something like log n step of random walk, a log of the logarithmic in the number of nodes in this graph, then you would like go to like a random spanning tree, or close to a random one. Yeah. And this is really now it gives you the algorithm. You start with any spanning tree. You do like this many steps of flip, a random flip, and you return that tree. So this is so simple, but like this is a deep theorem. I just want to say that, okay, like sometimes the fact that you can do random walk fast, like in logarithmic time, it gives you a polynomial time algorithm because the object you work with is exponentially large. This is quite cool. And by the way, each flip step can be done in logarithmic time using some data structure. So total time is like really small. Yeah. So this is a clean algorithm. And so we discuss this tomorrow, but so far we have seen basically, this is like the conclusion of the first half of the class. We have seen various ways to look at expander. So the first one is robustness. Can someone remind me what is this?
Delete the set of edges, then the smaller volume will be order of D over 3.
Yeah, exactly. Yeah. So, yeah, DH deletion. Yeah, deletion. Disconnect at most D over 5 volume. And exactly expander is really exactly an expander that satisfies this. For cut, we have seen that basically any expander, if G is an expander, yeah, expander G is basically cut equivalent to the product graph, where with the same degree profile. And also the same for flow. But this gives a bit more of interpretation. When you say that the graph is flow equivalent up to some log factor, it means that you can embed, like the excess of embedding of a graph into G, and vice versa. And this means that you can, for all the restricted demand H, you can embed H into G. Right. And by the way, we know that this is like up to log n factor by a flow cut equivalence. Also, the spectral view, this is just to say that this is big if and only if this is big, right? And the more precise relationship is by what? Yeah, right. And we have also seen that this, from the last view, this is also like within lock-in factor from the inequality that we have seen. And yeah, and this is basically mixing time is 1 over. And this thing is basically Shiger. Great. So yeah, this is quite beautiful. And so you have basically, but I want to make a point that most of the theory that you have seen is about conductance, which have relationship to lambda 2 and mixing time and so on. Conductance is about edge expansion, not vertex expansion. Although if the graph has constant degree, then edge expansion and vertex expansion are kind of the same. It's a kind of equivalent up to constant factor. And everything would like transfer to vertex expansion in that setting. But that is not like the case for general graph. So, but okay, this is about edge expansion and also in the undirected graph. So it's like people have tried actually to make like extend the theory for vertex expansion and in indirected graph. And yeah, this is another possible project if you want to just do some survey. Yeah. That's good too. All right, so any question before we skip to the second half of the class?
Are there results already proved in vertex expansion, or do we have to prove?
I think that like for this one, it's just about writing a survey, and there are some results out there. Yeah.
But is it as good as these many results?
So, as far as I know, I don't think so. So you still can have this equivalent flow cut equivalent, but I don't know like a good spectral view of vertex expansion. There are some recent paper on this, but I don't know enough to say. Yeah.
So sampling or spanning tree, is there any application where you would want to sample a spanning tree?
So yes, when there is like a kind of recent development on traveling salesman problem. So people got stuck at 1.5 approximation for a long time, right? And like very recently, that is like a 1.5 minus something like 40. Yeah, some constant. But before this work, actually, there is some improvement upon this based on random spanning tree. I don't know enough to say. Yeah. So basically, this one is essentially like it's called Christoph-Fides algorithm. Fides. And there are basically two steps. One is to compute MST, and then one is to compute matching. Now you just replace this thing by random spanning tree instead of minimum spanning tree. Yeah, and things get better. I don't know. Yeah. Yeah. Any more questions? All right. So next. So before we go to like algorithmic part related to expander, I want to tell you about two cute technique, which is quite new, but so powerful that it has found like a lot of application already in the past 2 years. So one is called local min cut, and one is called isolating cut. Both of them are like quite new, but yeah, powerful. So, so let me tell you first about local cut. So this is not about expander, but it's nice to see. Yeah. All right. Okay, so local min cut. By the way, is there anyone who didn't scribe yet? I actually forget to ask who would like to scribe the previous. You will. Okay, thanks a lot. Yeah. And how about this one about local min cut? Is there anyone who haven't? Or who would like to do it for a second time? Okay. So let me talk about this first, and then I ask you at the end of the class. All right. So maybe you change your mind because it's nice. Yeah. Okay. So local min cut. The motivation is that suppose you have the graph like this. It's just so big, and somehow you want to find something that you think of a cluster in the graph, but it's just too big. Even just to read the graph, you don't want to read the graph. And this is why we want to look at something called local clustering, where the setting is that you are given a graph, and then and also a vertex. Some vertex seed x here, and then the goal is that you want to find some cluster near x, right? But you don't want to read the whole graph. Like you kind of would like to just locally explore from x and get a cluster somehow. A cluster can be a lot of things, sparse cut or dense or something. So people studied, like this is a class of algorithm. But today we look at one specific problem. So, and by the way, the input model that I will assume that you have like a access to adjacency list on each vertex. Okay. The problem is, like the specific problem that we want to look at is this, where you are given a vertex x and some parameter nu, think of nu for volume, and k for size. Yeah. So two cases. So the algorithm either say that there is no set L that contain x, where the number of edges going out from L is less than k, and the volume is less than nu. So if there exists such a thing, then you think of it as like a cluster, where like it's kind of, you think like it's a cluster, small cluster containing x, and like it's weakly connected to something outside, right? Okay. But here it says that no such thing exists. That's the first case. Otherwise, it will return some set L such that the cut size is less than k. Here I just count edges going out, all right? And here the volume is not exactly like less than nu, but it's less than nu times k. So that's a problem. Is a problem clear that we want to look at? Now the point is that I'm gonna tell you how to do this in time, which is nu times k squared. It doesn't depend on the size of the graph at all.
Without this k factor, it's harder.
Without k factor, this is W1 hard actually. Like it's NP hard, yeah. But by W1 hard, I mean it doesn't even have like time, which is n to the k algorithm.
W1 is the approximation.
W1 hard is like it has even in the FPT setting.
Okay.
Yeah. So, I mean, no, if this is just new, exact, then no algorithm with n to the k time. So even if k is like some parameter to you, you cannot beat n to the k. That's what it means by W1 hard. All right, and this is just some motivation in real life. If X is infected, then maybe you want to remove like some connection between people, like prevent some connection. And it might be costly to prevent that connection, so you want to minimize the number of removal. But you also want to make sure that the people that still are risky, like the new volume here, is still small. So anyway, this is theory class. So okay, let's as a warm up, let me tell you like very simple case where I assume something super strong, but the algorithm is now very simple. And I'm gonna generalize it to general case soon. The simple case is this. Suppose that exists such an L. Suppose that exists such L like this. All right. A small cluster containing X, but and moreover, the number of edges going out of L is just exactly 1. And nothing go in. So it's like this. Okay. Then there is a super simple algorithm to detect such a cut L. Any guess actually? Maybe it's not super simple, but yeah. But let me explain. The algorithm is here. You just do some depth first search or breadth first search, anything from X. And let's say that you do it in such a way that you explore exactly nu plus 1 edges. So strictly more than nu. If you do that, you must go out of L, right? If you have explore more than nu edges, you will go out of L. And you will go out through this cut edge. And you will stop outside L. Now, what if we just reverse the path? Like, look at the vertex that you have stopped, and this gives you like some path from X to some node Z. What if we just reverse the path from X to Z? By reverse, I mean flip each edge here to something like this, and do this for every edge along here. Okay. So what is happening here? Well, the cut size will reduce from 1 to 0. Right? And now, suppose that you do the DFS again in the graph after you flip the path. What will happen? You will get stuck. You cannot go out anymore. Right? Because there is no edge, like this edge that the only chance that you can go out is now flip. So you cannot go out and you get stuck. And then wherever you get stuck, you detect such a set L. Make sense? All right. So now, that was a strong assumption when I said that there is no edge coming into L. What if there is such an edge, like coming into L like this?
Is it directed or I missed?
This is directed graph. Here, like we are really working on directed graph right now. If you will work on undirected graph, you can like create bidirectional edge for each undirected edge. Yeah. But if the graph is undirected, this situation will not happen, right? Yeah. And now we're gonna remove this assumption, but yeah, let's understand this. Like, what if there is an edge that coming to L, like this edge? Then the algorithm wouldn't work anymore. And the reason is that even if you have explored a lot of edges more than new, it might be the case that you will end up inside L. Like you go out and out and out and you come in. And if I reverse the path, then the cut size doesn't reduce. Right? So you will not get stuck basically after reversing the path. So that's the problem. But there is a idea, simple one, how to avoid such thing. Because we know that this set in any case is kind of small set. It's a set of volume nu, right? Do you have some suggestion? How do I avoid like end up like choosing a node inside L? And suppose that I have explored like maybe like, so this is new edges, and let's say I have explored like 100 new edges. What is the way to just getting some node outside L?
What is the L here? L we have to find, right? Or
Yeah, we assume that L exists. L is just a set containing X. L contains X, and the cut size of L is less than K, and the volume of L is less than nu. That's what we assume. And if this thing exists, I would like to return some set that if this thing exists, I would like to return some maybe L prime such that this is true, right?
How what about it's just a fraction of
Yeah.
to a factors to something.
Suppose that I don't require deterministic algorithm. So, yeah, something random, yeah. However, like we don't actually need random walk because, so let me tell you, like the point is just that, what if I suppose that I have explored like 100 new edges. I know that, okay, if I sample something inside, like let's say I just sample among all of the edges that I have explored, just sample one of them. Right? Then it's very likely that this edge will be outside because the edges that is inside they are just new, but I explore like 100 new. Then with probability like 1/100 at least, we'll get outside. 99%, sorry. 99% you get outside. So yeah, so you sample an edge that you have explored, one of them. And yeah, the edge might be here. And you can take like one endpoint of the edge. That one should be outside too. And then you don't really need that. The point is that now that you get some node outside L, you can just reverse this path, right? It's not need that you need to fix on the last guy that you have explored. I just really choose the random guy and reverse the path from X to Y. And if that happens, Y is outside L, then if I reverse this path, PXY, it would reduce the cut size by 1. So that's the idea.
What about this path is a simple path?
Yeah, so if it's not a simple path, then as long as the endpoint is outside, then you would still reduce the cut size by 1. So I argue about this formally soon. But now you have the general idea. So let me tell you the precise algorithm. It's gonna be simple. So you just repeat this for k times. First, grow some search tree from X. And instead of exploring 100 new, I say explore k times new, or 100k times new, something like that. And then if actually I got stuck already, I will just return the set that we got stuck. Like I got stuck at some, like you cannot continue the search. You got stuck at some set, return that set. And ignore this for a bit. Yeah. L prime is just the set of node read by DFS. And ignore this for a bit. But if we don't get stuck, then sample an edge among the one that we have explored and reverse the path from X to Y. And that's it. So if you just repeat this for k times, if one of the iteration you got stuck, you return a set. And otherwise, just terminate with no cut and declare that such L doesn't exist. Is the algorithm clear?
What do you mean by get stuck?
By get stuck, I mean that
The length of the path is less than k times mu.
no, I mean that you cannot explore k new edges. Like if
Yeah, and then you will run another algorithm to find the cut.
no, once we get stuck, it really like it gives you some. You just look at all nodes that you have explored.
Yeah.
That is a cut. That is some set. Then you return that set.
The path may go out of the cut.
The path. If you got stuck, you don't go out of a cut, right? So.
That moves k and you have reversed k times, so the path there is no outgoing. Right.
So just to be clear, when
So this path will not use a single step twice.
it might,
If it's a simple path or a path which can contain some loops.
you can assume that it's simple. Let's say that let's say you really like grow DFS tree, so it's a simple path. Yeah. It's important to maybe to say that once I have reversed the path here, and when I repeat, I repeat in a graph after I have reversed the path, right? It's a graph after this modification. And if an edge appears in the path twice, it would have reversed like again and again, flip back and forth. That can happen. But yeah, this is an algorithm. Any question before we analyze it?
Are there any differences between sampling and aging?
Say again.
Are there any differences between sampling and agents or sampling and the vertex of the tree?
So it's just that I define L to have small number of edges. So that's why I sample edge. If we know that L contains not too many nodes, you can sample a node.
How do we like do with the sampling just constant times gain instead of k times?
Why K and not constant? You mean?
Because we are repeating k times.
Yeah, because we would like to be outside for K times. So the probability would be good enough if you make it K. So let you see analysis very soon. Yeah.
So this case shown in the picture is bad for us, right? Because it would just, like if it again ends up in L, what do you say, the path.
No, this is not bad for you because even if you end your search here, you sample an edge here,
Okay, in the path.
and you just you reverse it from the sample edge, and it's likely that you sample an edge outside L.
Okay. So we are reversing only after white, only before white, right?
Yeah.
You explore exactly k times new edges. It is not just a path, it is a tree, right?
Yeah, it's a tree.
Oh, it's a tree.
It's a tree. Yeah. Right. Yeah. So yeah, you kind of you just explore here and here and here and maybe here, and you and this guy might be like might have some more edges here, right? So you really just look at the volume of the set you have been exploring. So this the total number of edges here is at most nu times k. And then you take one node, one edge inside this set, and and take like, call it y and y prime. Oh, so take that as your y prime edge. Okay. All right. So let's analyze this. Well,
If I explore a domain, like when we do DFS tree, you might visit some visited node. Does that help
you count that as an edge that you have explored.
with like a DFS tree with some extra edges?
Yeah.
Like on the DFS tree vertices, whatever edges, even the curves.
Yeah, you count all of that. So doing this, because you really spend time proportion to the number of edges that you have explored. So you need to count the edges not in the tree edge too. Yeah. And this is really why, because you repeat k times, and each of the time you explore new times k. This is why this is a running time. It's new times k. K times new k, which is new k squared. So that's the running time. And there are two things I want to tell you. First, if it does return some cut, L prime, this is a cut in the modified graph, right? I want to say that this cut actually is a good cut that we want in original graph. So in original graph, you will, if L prime is returned, in original graph, you have that the size is at most k and the volume is at most k nu. And also, I will prove as well that if L exists, then some cut L prime will be returned. Our algorithm will return some cut with some probability. It's constant probability, but you can always boost this just by repeating log n times. Okay. So the time is easy to argue. Let's look at this claim. So note that if L prime is returned, then there were less than k path reversion happen, right? Like at most k minus 1 path reversion that we have done. And let's analyze it a bit. If you fix an L prime that contains x, and if you reverse the path xy, if y is outside L prime, then you know that exactly the cut size will reduce exactly by 1. Just because, yeah, even if you go like cross this cut many times, the number of times that you go out of a cut will be 1 more than the number of times that you go in. So when you flip, then the cut size reduced by 1. And if y is inside L prime, then you also know that the cut size really stay the same. Yeah. But what does it say it means here? It means that if at the end of the algorithm, the cut size from L is 0, and there will strictly less than k path reversion, then in original graph, the cut size of L in original graph is strictly less than k. Okay. Question? All right. And also, so we have this, and why this is the case, why the volume of L prime is less than k nu. Yeah. Like we explore this many edges Although like the direction of edges change, but it's the same volume. Okay, so yeah, I forget to say that the volume count all edges incident to the set, both in and out edges. Yeah. But yeah. Okay, so the last thing I need to say is that if now L exists, then we will return some L prime. Okay. So look, L have volume less than nu and the cut is less than K. And now so now we have that when you sample Y will be outside L with probability this much, right? Which is 1 minus 1 over K. And if this happened, the cut size decreased by 1. And so after K minus 1 iteration, like the probability that this event keep happening at every iteration is just this much, which is at least 1/10. Which means that in the last iteration, you would get a cut already, because the cut was less than K, and you reduce the cut size at every iteration. So yeah, it means you will return some cut. Question about the analysis. Okay. All right. So if you think about it, this is kind of localized version of Ford Ferguson. Yeah, just to conclude, you can solve this problem, some kind of local clustering problem in time which is independent of n. Okay. So that is one algorithm. And now, okay, let's go to, and actually you can use this algorithm to solve some cut problem where, like, suppose that you have a directed graph, and so directed graph G with m edges and n nodes, and you want to find if there is some cut, like any cut at all, such that the number of edges going out is less than K. So this is like a global min cut problem, but in directed graph. Yeah. And yeah, the trivial algorithm to solve this is just to fix some source and run like st min cut in G and in the reverse graph. So that takes n max flow time, like n max flow call, which is like quite slow. But using the local algorithm that I mentioned, you can actually improve it to mk square. I will talk about this tomorrow. I will skip to the another technique. And by the way, there is another algorithm that takes mk time. It's much more complicated, but it's better. But the nice thing about this algorithm is that it also works for vertex cut too. And this is the best known if you talk about vertex cut. And even in the undirected graph, it's the best known too. Yeah. Okay. So that's one technique. Yeah. Now I want to talk about another technique called isolating cut. So in this case now we are look at undirected graph. Okay. And so you have a graph G and some terminal set T. Some sort of terminal set T. And what you want to compute is that for every node in the terminal, you want to compute V and TV min cut. So it's a min cut that separates V and the rest of the terminal. Yeah. And you want to do this for every V. So like there are T many cuts that you want. And it's clear, like, and by the way, I will just call this cut minimum V isolating cut, because it isolates V from the rest of the terminal. And actually any V TV cut is like is a V isolating cut. And the trivial algorithm is just to call MaxFlow for each V. Right? That is like if you have this as your terminal, this is V, then you can like connect S here and then connect the rest to T, and you solve MaxFlow. And you get some min cut. So that takes T MaxFlow. And actually, it turns out that you can do it in logarithmic many MaxFlow. Okay. And now let me describe the algorithm. It's actually quite simple. So the algorithm is this. Let's give a name to each node in T using binary string of log T bits. Okay, and now focus on each bit I, like start from I equals 1 to log T. Then you say that for each terminal you recolor a node red if the ith bit is 0, otherwise it's blue. So like if you have this terminal, you just 1/2 is become red, 1/2 become blue, right? And then, so this is a red guy, this is a blue guy with respect to ith bit. And you just compute the min cut separating red and blue. And let's say this Ci is a min edges crossing the min cut. Right. So now know that if you do this for every cut for every dimension, log n many bits, log t many bits, then you get Ci for every I. And if you delete these cut edges, like if I find like a first cut, and so if there are four terminal, then there will be like 2 cuts, right? If I remove these cuts from a graph, it will partition a graph into parts. And for each terminal, I can define UV to be the part that contains V. And then it's kind of clear actually that UV will contain exactly V and nothing else, no other terminal. This UV really separate V from the rest. And it's kind of clear from picture, but the reason is just that if UV actually contains 2 nodes, V and V prime, like from the terminal, then there must, like V and V prime have different binary string that represent it, right? So one of the bit will differ. And it means that let's say the I speed differ. So actually CI would separate V and V prime and cut through UV. So that cannot happen. So UV contains exactly V. Okay. So at least UV is V T minus V cut. It's an isolating cut. But it might not be a minimum one. Okay. So what do we do? So let's say that lambda V actually is a size of the mean, like size of mean cut. That separate V from the rest. So the size of UV might be more than it might be possible. So UV might not be good yet, right? But the point is this. Let's define S star V to be actually the minimum V isolating cut. So it's the V T minus V mean cut. But it's a one which is inclusion-wise minimal. By which it means that if you take any SV which is VTV mean cut, VT minus V mean cut, then this guy is always a subset of SV. It's an inclusion-wise minimal guy. So I am going to claim that actually this exists first. That there actually really exists a unique cut which is inclusion-wise minimal. S star V exists. Okay. So suppose that is true. The next thing I'm gonna, like the key lemma is that actually S star V is actually contained inside UV. So we're gonna prove this. But suppose this is true, then it's gonna be good for us now. The reason is that, well, as a last step of the algorithm, for each of the terminals V, what you can do is that you can contract everything outside UV into one node TV. Right? And let's call this graph GV. And then you can compute like V and TV mean cut. And you will get some cut SV. So SV gonna look like something like this. It might be S star V exactly, but it will at least it will contain S star V at least. So is the algorithm clear?
So just to be clear, UV is a subgraph, right?
UV is a subset of nodes.
Subset, no.
Yeah.
When you say like, yeah, can you remind me what is a min cut again? It's a set of edges or a set of?
It's a set of nodes. Yeah. So again, so we start from terminals, right? And we partition a terminal into two parts in log n many ways, like log t many ways. For each of the time that we like when you partition it in one way, you get some cut. So I define Ci here to be edges crossing the mean cut. Okay. This the green thing is the edges crossing mean cut. And we define like And then once you have compute Ci for every I, then you delete all these edges from Ci. You would like partition the graph into like parts, basically. And UV is just the part that contains V. Are you with me, or?
I mean, I get you partition it into connected components, and you're saying like ignore some connected components, just look at the one that contains the.
Yeah.
Okay. I see. Okay, that's.
So for you have a lot of parts, but like for each terminals V, there is a part that contains it, and we call that part UV, right? And we have two things. That is, if it contains a terminal V, it would not contain any other terminal. That's one thing. And moreover, the very important thing is that I'm gonna claim that the min cut that separates V from the rest actually is safely preserved inside UV. It cannot be like S star V cannot be like this. It cannot be like this. It is inside UV here. Is the claim clear? Yes?
Minimizing the cut size or the conductance.
Oh, this is really about cut size, yeah, not about conductance.
And then what if the cut is just V itself?
It can be the case. If the cut is V itself, then trivially it is inside UV, right? Because this cut is inside this. Yeah.
In which case, would say why is that not the main one?
So could you repeat what's the last step once we know this whole?
Yeah. The last step is that I look at UV and I really just contract every node outside UV into TV. And then this become one node. And now we're gonna compute min cut between V and TV. Compute min cut between these two nodes. All right. So
But that still doesn't get you like SV star.
So what we want is like just some min isolating cut. You don't need to get minimal inclusion-wise minimum isolating cut.
Okay, sure.
Yeah.
Wait. So I'm sorry, I just confused. So we're still talking about, so cuts are vertices, right? That's what you're talking
Yeah.
about, sets of vertices.
Yeah.
Okay, so yes, there could be, the sizes of the sets S star and SV are the same, but they could be different. That's what you're saying.
Right.
That
Right.
makes sense, yeah, perfect.
Yes.
Good.
We try to minimize the cut size, and to like S star V is just the guy that have minimum cut size but minimal number of vertices. Yeah. And it helps us to analyze things. Yeah. We don't need to find it.
Does this inclusion one property also the pages are weighted?
Yes. Yes. All right. Okay, so I'm gonna claim now that like once you compute SV here, it is a minimum V isolating cut. That is a V TV T minus V min cut. All right.
That's the question. Sorry.
And so yeah, why is this V isolating? Because it's inside UV. UV isolate V already. So if it is inside UV, it's going to be isolating. And why is it minimum? This is because S star V inside GV here, inside this contracted graph, is also VTV min cut. It's also VTV cut. It separates TV from V. But we really compute V and TV min cut. So this guy, the cut size here is going to be at most the cut size of S star V, which is at most this. So SV really is minimum V isolating cut. And let's analyze the time. Well, the time is going to be simple. That is, for each of the dimension I, like to compute CI, like edges crossing min cut CI, you take one Mach flow. So that is log n Mach flow, like log T Mach flow. And okay, once you have computed that, then you compute one Mach flow in GV. So now there are actually a lot of Mach flow. But what do you know actually? So it's true that you compute one Mach flow in GV, but the total size of GV is going to be at most the total size of the graph, maybe times 2. Because each edge appears in at most 2 parts. Right? So if an edge is inside here, then it appears in just one part. If an edge is here, then it appears in like 2 times when you contract. When you contract everything here, and when you contract everything here. So each edge appears in too many GV. So the total size is this. So you can think of it as like, okay, many Mach flow, but the total size of that Mach flow is just original graph. So you can count it as one Mach flow actually. By the way, you can actually really simulate calling Mach flow on every GV simultaneously, just by one Mach flow call. Actually, you can think about that. Yeah. So it remains to prove this. Why? How come? Like this minimal thing, the unique minimal guy exists, and why it is inside UV. But before that, yeah, I want to ask you again about running time and like the description of the algorithm. Is it okay? Okay. All right. So the thing that you need to know, the only thing that you need to know is submodularity of cuts. So if you have any set A and B, then the cut size of A intersect B plus the cut size of A union B is at most cut size of A plus cut size of B. So when the function on set certify this thing, you call that function submodular. And now this function is the cut size, and this cut function certify this thing. So we say that this cut function is submodular. And you can just verify it just by drawing thing. And you will see that well, cut size of A, then you count this case where you go from A to outside. And yeah, I let you verify it. Yeah. So actually, if there is no edges between like this thing and this thing, if there is no edge between A minus B and B minus A, there is no like this kind of edge, then they actually will be exactly the same. But because of this crossing edge, this is why it's submodular instead of modular. And it's important that this actually only work in undirected graph. This is the part where we exploit undirectedness. Let me talk about this in the exercise session. But now, suppose now that A and B are ST min cut. So let's say A and B, ST min cut, and let's say S is here, T is here. Then do you see why both of them here must be min cut too? Well, the reason is just that both, okay, let's look at here. Suppose that A and B are ST min cut, right? You also know that this guy and this guy, both of them are ST cut as well. They are ST cut. So it means that this is true. Like, it's some ST cut, so the size is at least the size of ST min cut. And so you can conclude that actually both of them, like everything is actually the same. Yeah. And now it means that there must exist a unique inclusion-wise minimal guy. Why? Because if actually there are two incomparable guys in two incomparable sets that are min cut, if you look at just take the like a intersection, that's min cut too. So you can keep going and going. There must exist a min cut, yeah. Like a minimal guy. The last step is just here. How come the minimal min cut is in UV? Well, let's look at here. So actually it suffices to prove this. That is, so did I have some picture? No. So let's say that this is V, this is S star V. Okay. It suffices to prove this. That is, if I just look at one cut CI, I just need to say that this part cannot exist. If this is true for one CI, then if it is true for every CI, then it means that SV must be inside UV, right? So I just need to look at one dimension, basically. Okay. So let's call this part X, this part Y. Yeah. And then let's assume for the contradiction that this thing exists. So it is not a subset, so this part exists, right? And now we just write this submodularity inequality of a cut. So this is X is just this part, and you look and have S star V in this. Okay, now look at the intersection.